SwayamPrabha. Digital India. Educated India.
Hello all, welcome back to this course. We are on week 11 where we are continuing our discussion on the macro mechanics of the laminate. So in this video, we'll be starting to look at select laminates. So in the composite industry, there are few laminate sequences which are commonly used. So we'll focus on those select laminates and see how we can apply the classical laminate theory that we discussed in the previous week and get some idea about the stiffness of these select laminates. So here is a quick review for the classical laminate theory. Essentially, we have introduced these three matrices A, B and D. Using these three matrices, we are able to relate the normal forces as well as the moments with the midplane strains and the curvatures. So, and here are the names for the ABD matrices. For the A matrix, we call it as the extension stiffness because it is connecting your normal forces with the extensions in the mid surface. And B is the bending extension stiffness where it connects the normal forces with the curvatures, or in the second equation, it connects the moments with the uh, extensions in the mid surface. And regarding the D matrix, we call it as the bending stiffness. So as we can see here, it connects your bending moments with the bending curvatures. And here are the expressions where we write these terms of the A, B and D in terms of Q dash. What is Q dash? Q dash is our transformed stiffness matrix of the lamina. And Zk and Zk minus 1 are the coordinates of the top and bottom of the lamina. So now let's focus on this transform stiffness matrix and see how these values vary, whether it is off-axis loading like angles other than 0 and 90, or if the angles are 0 and 90, how this matrix simplifies. So we'll look at these stiffness matrices of the lamina. First, we'll start with the relation between the stress and strain when we are working in the material coordinate system. So 1, 2 is the material coordinates where direction 1 is along the fibers and 2 is perpendicular to the fibers. So in this, we get the stiffness matrix where the Q16 terms and the Q26 terms go to 0. What does this going to 0 mean? These are the extension shear couplings. So they going to 0 means when you apply a normal load, there is no shear strain. Or if you apply a shear stress, there is no corresponding normal strains. But if the orientation angle instead of being theta is equal to 0 or 90 degrees, we can directly use this material coordinate systems relation between the stress and strain. But if we are talking about off axis, meaning theta which lies between the angles of 0 or 90, then we use these stress strain relations in the body coordinate system, where we use xy for the body coordinates. These are the stresses in the body coordinates and the strains in the body coordinates. These are related using this stiffness matrix Q dash, which we call it as the transformed stiffness matrix. So these we represent with a Q with a bar. But now the question is, these values of the transform stiffness matrix depend on the material we are using, which means the material properties as well as the orientation. So let's quickly look at what is the relation for each of these components. So these are like lengthy equations for each of these components. The idea here is not to show the equations, but there is something interesting we can learn from these equations, and that's what I want you to focus on. Please don't get carried away with these lengthy equations. Now let's focus on the first equation Q11. The idea is to see how will this change whether the angle is plus or minus. So let's say we are talking about Q11 for an angle of plus alpha. How is this related if the orientation angle is changed to minus alpha? So if you notice, the cos terms are power 4, meaning plus or minus won't have a difference. And here too we have sine square and cos square, as well as finally we have the sine power 4. So because of these even powers of sine and cos, no matter whether the angle is positive or negative, these values will be the same. Q11 for minus alpha. So what we mean is, let's say we are focusing on two different layers in the laminate with the same material. Since it is the same material, we will have these Q1 terms, Q12, Q66 and the Q22 terms the same. The only difference will be the orientation angle alpha. So let's say we are looking at two plies, one with plus alpha and one with minus alpha. Now we are trying to see how different is this transform stiffness matrix. So we showed here for both plus and minus we get the same value. Now let's move to Q12. So here too, if you notice, we have even powers for sine, cos square, sine power 4, cos power 4, which again means we'll end up with the same value Q12 bar even if the ply orientation is minus alpha. Same thing can be said about Q22. But now when we look at Q16, then we see that this power for the sine is 1, power for the cos is cube, and here too we have cos and sine. So what it means is, if you these values will be different for whether the lamina is orientation of plus alpha versus minus alpha. And the relation is Q16 bar for plus alpha will be minus of Q16 with minus alpha. And this minus is coming because the sine and cos have odd powers to them. But the rest all the terms remain the same because we are looking at the same material, meaning the same stiffness matrix Q. So Q11, Q12 and Q6 remain the same. The only difference is the angle. Now we see these are different. The same repeats with Q26, meaning the Q26 value as plus alpha is minus of the Q26 value for a lamina with minus alpha. And lastly for Q66, again we notice that there are even powers for sine and cos. So the differences, the plus alpha and minus alpha will give the same value. So Q66 for plus alpha will be the same as Q66 bar for minus alpha. So the take home point from here is, or the where we have to stress is these values of Q16 and Q26, because only here we see that if the angle changes from plus alpha to minus alpha, these terms have a negative sign. But for the rest of the terms of the stiffness matrix, they remain the same. This will get back to some special laminates which we'll be discussing later. So I thought we'll discuss about this and make this observation. Okay. Now let's start looking into some select laminates. One of the very commonly used laminate is a symmetric laminate. As the name says, it is symmetric, meaning we'll define it like this. So we say that both the geometry and the material properties are symmetric about the mid surface. So here is the pictorial representation. Let's say this is the mid surface. So about the mid surface, let's say we are considering two laminas. Let's say this is a kth layer lamina, and corresponding to this there is a symmetric lamina, meaning they both have the same geometry. What does geometry mean here? Both have the same thickness and the same orientation. And we also say both are of the same material properties. So let's say if this kth layer is made up of GFRP unidirectional lamina, even this top layer is made up of the same material unidirectional lamina. So meaning the ply material is the same, orientation is the same, as well as the thickness is the same, and they are placed equally from the mid surface, then we call this as a symmetric laminate. So here I only showed a pair of lamina, but we can call it a symmetric laminate if all the plies in the laminate follow this principle, where there is symmetry for both geometry as well as material properties. Now let's see how the AVD matrices change. So we'll focus on the B matrix because here we see there is a great deal of simplicity we notice. So let's focus on this formula. So we said Bij is half times summation of layers going from 1 to n, the components of the transform stiffness matrix times Zk square minus Zk minus 1 square. So let's focus on how do we write these terms. So let me erase this first, and then I should be able to show this Zk and so Zk is always the bottom face and Zk minus 1 is the top surface. And we know in the laminates the way we are defining Z is going downwards is positive Z. So this will be Zk minus 1, and for the bottom we have it as Zk. Since both layers are symmetric, let's say if we already know Zk minus 1 and Zk, what are these values? They both will have the same magnitude but opposite sign, meaning this will be minus Zk minus 1 and minus of Zk. Okay. Now let's plug in these values into this formula and see what does it result. So let's say we are only focusing on these two layers. So it will be 1 by half, and this transform stiffness matrix will be the same because of the symmetry. We said both are the same material, same thickness, same orientation. So this Qij or the transform stiffness matrix will remain the same for both layers. Times, let's start with the kth layer. So whenever we say Zk, we are referring to the bottom of this layer and then the top of this layer. So bottom of the layer is Zk square minus Zk minus 1 square. So this is for the bottom and top of the layer. So this is for the kth layer. So let's now call this the symmetry of this kth layer as the lth layer. Then we should now write it as starting from the bottom. Bottom of this lth layer is minus Zk minus 1 whole square minus top of the lth layer, which will be minus Zk square. So this is for the lth layer. So again, let me point out this is for the bottom and this is for the top of the lth layer. So once we expand this, so it will be Zk square minus Zk minus 1 square plus, since there is a square for this negative sign, it will be positive Zk minus 1 square. This negative will write it here, and minus Zk square will be Zk square. Okay. So now we can see that these two terms cancel out first and then these two also cancel out. So in effectively what we found is this value is 0. So the Bij value or the B matrix goes to 0 for a symmetric laminate, and here we have shown it why it goes to symmetry. Here we have only showed with one pair of symmetric laminates, but this can equally be applied to all other pairs. For all other pairs, these values cancel out each other, so the B matrix is 0. What does that mean? So there is no extension bending coupling. So what it means is when we apply the in-plane loads, we will not have bending and twist curvatures. What does this mean? So when you are applying this n equals a times the mid surface extensions plus b times b matrix times the curvatures. Since b matrix goes to 0, we are saying that the in-plane loads are directly related with the extensions in the mid surface and they are not related with the curvatures. That's exactly what it is said here. And we can also show with the second equation that bending and twisting moments will not give extension of mid surface. So when we write the second equation for moments, we write it as b times the mid surface extensions plus d times the curvatures. Since the B matrix goes to 0, we are saying when we apply moments, what we see are curvatures. So there is no bending extension coupling. Or in other words, when we apply moments, we don't expect to see extensions in the mid surface. Since we don't have this extension bending coupling, symmetric laminates are very commonly used in the industry because it makes the analysis simple. Not just that, but it also makes the manufacturing simple in some cases. For example, when we prepare molds and when there is changes in the temperature, let's say during curing, then because of these coupling between the extension and bending, there will be change in the shape of the cured laminate. But once we have a symmetric laminate, one can avoid those changes in the shape because of the change in temperatures. Now let's see how we can apply this symmetric laminate to other few select laminates. So now we'll start discussing about a simplest of the laminates called as specially orthotropic laminate. Though we call it as a laminate, it is basically a lamina, meaning it is just one single layer of specially orthotropic laminate with a thickness of T. So now the question is, how do we apply this CLT to get the ABD matrices? So here are the expressions we know to get the components of the ABD matrices, but let's apply and see if there is any simplifications we can see. First, let's start with the B matrix. So looking at this, we should identify that this is a symmetric matrix, symmetric lamina, because about the mid surface, let's say we divide this single layer into two halves, two equal halves of equal thicknesses. Then we can say now it is a symmetric laminate because the top half and the bottom half are made up of the same material, same thickness, and same orientation. We have just seen that for a symmetric laminate, the B matrix goes to 0. So similarly for this specially orthotropic laminate, we can say that the B matrix goes to 0, meaning that there is no coupling between the extension and bending. Next, how can we write the A matrix? So A matrix can be simply written with the Q matrix times thickness. Let's see why we do this. So let's write the Z values. Z values, as we know, are positive going downwards, meaning at the bottom surface we have it as plus T by 2 and the top surface is given by minus T by 2. So let's say we apply this formula here for Aij, and since the n value is 1, k is equal to 1 to n, we can get rid of the summation. It is simply Q dash. But here we need to say that we are talking about a specially orthotropic. Why do we call it specially orthotropic? Because the coordinate system we are choosing is aligned with the principal directions, which are along the fiber's 1 and perpendicular to the fiber's 2. In that case, instead of writing the transform stiffness matrix, we can simply write the stiffness matrix. So instead of Q bars, I can simply write it as Qij. So which means we are talking about angles either 0 or 90 degrees. Okay. So we are following with this first equation. So Qij times Zk minus Zk minus. What is Zk? the Z value for the bottom of the surface, which is plus T by 2, minus Zk minus 1, which refers to the top surface, so which is minus T by 2. So we see that this is simply T times Qij for the kth layer. So here I can remove the kth layer because there is only one layer. So it is T times the component of the stiffness matrix. Okay. Now let's move to the D matrix and see how we can write it for this laminate. Again, we notice that the Q matrix remains the same. The only difference is here. And again, from this equation, let's see how we got this T cube by 12. So again, Dij is written as Qij times, for the bottom surface, Zk, which is T by 2 whole cube, minus for the top surface, which is minus T by 2 whole cube. Yeah, I should add a 1/3 here. Okay, now let's substitute and see. This should be 1/3 of Qij times T cube by 8 minus, since we have a cube and it's a negative, so we'll still have that negative, minus T cube by 8. This can be written as 1/3 Qij times, it will be T cube by 4. Effectively it is 1 by 12 Qij times T cube. So here we get this T cube by 12, which we place it here, and the rest is we directly get the stiffness matrix Q. This should explain how we got these ABD matrices. The important points to note are, first, the B matrix goes to 0, meaning there is no bending extension coupling. And secondly, if we notice here, our extension shear coupling are also going to 0, meaning that there is no extension shear coupling. And similarly here again we have this. What does this mean? There is no bending twist coupling. Okay. So I hope this is clear. Now let's move to the next laminate, which instead of using the specially orthotropic, we now have the generally orthotropic. What do we mean by generally orthotropic? Meaning the angle is neither 0 or 90. In fact, it is off axis, meaning at an angle theta. Since it is at an angle theta, when we start writing for a lamina the stiffness matrix, we should work with the transform stiffness matrix Q bar. So here are again the expressions for the ABD, and here too let's see if we can simplify these ABD matrices. First we notice that there is symmetry since we are only looking at one layer, and if we consider the half thickness as the mid surface, then again we can write these Z values as T by 2 minus T by 2, and since there is a symmetry, we can simply say that B matrix goes to 0. There is no extension bending coupling. Now coming to the Aij matrix, here things are very similar to the previous slide where we discussed about specially orthotropic. The only difference being, since we are working with generally orthotropic, now we work with Q bar, which is the transform stiffness matrix. Earlier we simply wrote Q matrix, the stiffness matrix, because the angle is either 0 or 90. So here we still get this T, and this transform stiffness matrix is what we are looking at. Okay. Same thing goes with the D matrix. So like previous slide, we have this term T cube by 12, and here we have this Q bar. Since we are working with a generally orthotropic, we have to work with the transform stiffness matrix Q. So now let's summarize what we have discussed in this short video. We did a quick recap about classical laminate theory, as well as we have also looked at how the stiffness matrix looks for a lamina, both for the specially orthotropic lamina and the generally orthotropic lamina. And then we started discussing about few select laminates. We started with the symmetric laminate, which is very commonly used in the industry. And the salient points we have seen is, first, the B matrix goes to 0 for a symmetric laminate, meaning there is no extension bending coupling. And then, using this as a background, we started looking at the specially orthotropic laminate. Since it is a single layer of specially orthotropic lamina, we said this is a symmetric, meaning this too will have the B matrix going to 0. And then for the A and D matrices, we said instead of writing in terms of transform stiffness matrix, here we can write it as, since theta is 0 or 90, we can write it in terms of the stiffness matrix Q. So for the A matrix, we said it is simply T times Q, and for the D matrix, we said it is TQ by 12 times Q. Moving to the generally orthotropic laminate, where we said the only difference now is theta is an off-axis angle. So, but again, here too the B matrix goes to 0 since it is a single layer, and we can consider the half thickness as the mid surface. And then considering the A matrix, we said again it looks like the previous specially orthotropic laminate, where we write it in T times Q. But instead of Q, here we need to write it as Q bar, because it is an off axis, meaning we need to look at transformed stiffness matrix. For the D matrix, it is T cube by 12 times Q bar. So essentially what we are trying to start to show here is, when we consider these select laminates, the reason why we choose these mostly in practice is because they give some benefits. Starting with symmetric laminates, we said the B matrix is 0, there is no coupling between extension bending. But coming to specially orthotropic laminates, we showed that few of those couplings go to 0, like the shear extension coupling and the bending twist coupling, there is goes to 0. So which means there is no extension shear coupling, neither there is bending twist coupling. So, but in the generally orthotropic laminate, both these couplings are existing. So both the extension shear as well as the bending twist couplings are present in the generally orthotropic laminate. So here we just started with the special laminates, but actually there are few more interesting laminates which we'll be discussing in the next video, and which are again commonly used in the industry, and we will look in next class about why these select laminates are commonly used. Until then, thank you.